Hi everyone, Jason from Makera here with another project tutorial, and in this one we're creating another fidget toy, but it's a metal fidget spinner using the Carvera and Makera CAM. Using the Fidget Toy Tool Kit available in our store, you can manufacture a wide range of fidget toys using your desktop CNC and the materials and bits included in this toolkit. In this tutorial, we look at how to make a classic fidget spinner, though with a multi-layer twist, which will involve some intricate toolpath design for a multi-sided metal project. You can choose to design your own CAD files for this project, or you can download the 2D CAD files that I'm using in this tutorial from the knowledge sharing page on our wiki site. You can also download the CAM files pre-prepared, but in this tutorial, we're going to walk through how to create this project in Makera CAM step by step. So let's get started. All right, so after launching a new design file in Makera CAM, the first thing that we want to do is set our stock size. So we're going to hit the edit button and we want to select aluminum unless you've chosen to create the spinner using a different material, which is perfectly fine. And we're going to set our size to match our stock. In my case, it's going to be the 100 by 150 by 5 millimeter piece of aluminum that comes in the Fidget Toy Tool Kit that you can grab from our store. Next, we need to import the design file for the top of our fidget spinner, which you can download from the knowledge sharing page. And we should see all parts of our design loaded right here on a new layer. Now, if we wanted to, we could reposition this file, but it should already be set based on this stock size with an appropriate margin all the way around. With that, we can start by creating our first toolpath, which is going to be our pilot holes for our flip of our stock. So I'm going to hold Shift on my keyboard and select all 4 pilot holes here, then create a new vector drilling toolpath. We're going to drill from 0 millimeters to 7 millimeters. That should be enough of a margin to drill through the stock and also drill into our wasteboard so that we can insert our alignment pins. And we want to select our tool. I'm going to go to my drill category and select a 2 by 12 millimeter drill bit. Aluminum should already be set as the parameters because we've set aluminum as our stock earlier, or whatever material you did choose to set. And we don't have to adjust any of the parameters. The default should be fine, but you might need to change your tool number if you're using the Carvera and you're using a different slot than what the default is. For example, I have this loaded in tool 4 on my machine. Lastly, we do want to enable a retract. I'm going to do a fixed Z height of 1 millimeter, which means that it's going to do a peck drilling function, retracting as the process is completed to allow for proper chip evacuation. We can then hit calculate and we'll see both that the path was created and our little path icons for a drilling path. Next, we're going to create a vector pocket for these intricate designs. I'm first going to select everything that I need, then go around while still holding Shift and deselect anything that I grabbed by mistake. So the only thing we need are our triangular designs here to engrave in this next toolpath. With those selected, we're going to go ahead and create a vector pocket toolpath. Our start is going to be from 0 and our end depth is going to be 0.3 millimeters. You then may need to change your bit depending on what you're using. I'm going to use the 0.3 millimeter engraving bit from our toolkit and make sure again that aluminum is set as your parameter if that's the material that you're choosing. If you had another bit in this pocket toolpath previously, you may need to delete it so you only have one for this simple clearing path. The default parameters should be fine, but again, you might need to adjust your tool number depending on the order that you're using this bit, or if you have your tool loaded in a certain slot in your Carvera as I do, so I've set this to tool 3. Our default strategy settings should be fine, but we do want to make sure that we enable ramping. And for this, I'm going to enable a ramping distance of just 5 millimeters with an angle of 10 degrees and a start height of 1 millimeter, which should give us a nice clean cut while also protecting the end of our bit. We can then hit calculate and see the toolpath generated. I'm going to hide this pocket process, and next we're going to create the pockets for the magnets and the bearing. So I'm going to hold Shift on my keyboard and select all 8 magnet holes like so. And then I'm also going to select the 2 bearing holes, which are these 2 outer holes here like that. We can then go ahead and create a new vector pocket toolpath. And we're going to start from 0 and end at 2.2 millimeters for the height of these components that we're working with. We want to change our bit from the engraving bit, so I'm going to delete that. And instead, I'm going to add from my single flute metal category a 3.175 by 12 millimeter flat end mill with aluminum set as my parameters. The default parameters should be perfectly fine, but you may need to adjust your tool number again. I'm going to change this to tool 1 based on where I have this loaded in my Carvera. And we also want to again enable ramping. I'm going to use the same parameters as before, so 5 millimeters with a 10-degree fixed angle and a start height of 1 millimeter. We can then calculate these toolpaths, and we will now have our pockets created for these crucial components. Next, we're going to create a pocket for our post that's going to hold our spinners together, and that's going to be in these two end cap holes. So I'm going to select the two inner holes here and create a new vector pocket toolpath. For this, we're going to start from 0 millimeters and end at 3 millimeters. We're going to use the same 3.175 by 12 millimeter end mill, and we're going to use the same parameters, so none of these settings should have to be adjusted. Likewise, the ramping strategy also will remain the same, so you can simply calculate this toolpath to create it. While we're still working on our two end caps here, now we're going to machine material away, which will reduce the overall height of these end caps, giving us a nice flat piece, while also making a post around the hole that we just created in the center. So to do this, we're going to select the outer circles on both sides and the larger circle from within, like so. We can then create a pocket toolpath and set our end depth to be a little bit more, so 3.5 millimeters, so we get a nice overall thickness at the end, as well as create a nice post that goes around the center hole that we've created. But we're going to keep all the other settings exactly the same. In your strategy, we want to create an offset strategy with inside out as before, but this time we're actually going to also offset the cut negative 0.1 millimeters, so that way we have a nice post here as we go ahead and create this cut. As with before, we can enable ramping just to keep the wear on our bits low, and we can calculate this toolpath. Next, we're going to cut the outer perimeters of all of the different shapes, but we're not going to do this to cut all the way through. We'll do that after we flip our stock over. Instead, we're just going to cut the perimeter, which will do most of the machining and allow us to create a chamfer while still on this side of the stock. To do this, I'm going to select all 4 outlines around all 4 different parts, like so. We can then create a contour toolpath, and our start depth will be 0, and our end depth will be 4 millimeters, which means that there's only 1 millimeter remaining between this bottom of the stock and these parts, and we need to keep that in mind for later when we flip our stock over. For our tool, we're going to select our single flute 3.175 by 12 millimeter flat end mill for metal with aluminum set as the parameters. You shouldn't have to change the parameters at all, but you may need to change the number of this tool if you reassigned it earlier. Next, we don't have to change anything in our strategy. We're going to cut on the outside as per the defaults. We are going to enable ramping again, but we might need to reset our distance to match what we did earlier with a distance of 5, an angle of 10, and a start height of 1. And we're not going to need any tabs as this isn't going to cut all the way through. We can then hit calculate to see our outer outlines profiled. And the last toolpath we need for this cut, and I'm just going to hide all of our other paths, is a chamfering path. Now the chamfering path is going to follow the same lines that we just used before. So I'm going to select my 4 outlines again, and it's also going to be another contour toolpath. This time, however, our end depth is only going to be 1 millimeter. We're going to change our tool to be our chamfering bit for metal, and I'll be using a 0.1 millimeter by 90 degree chamfering bit, which is included in the toolkit, as well as an aluminum preset for this. And we are going to adjust the default parameters. I'm going to change my step down to be 1 millimeter, which means that there's only going to be a single pass, which will give us a nice clean cut. But to do this, I'm also going to drop my feed rate to 100, my plunge rate to 100, and if I need to, change my tool number, which in this case I do not. We're going to use offset as a path strategy, and we need to offset the chamfering bit negative 0.5 millimeters, which is what controls the size of our chamfer. Ramping is incredibly important as we're doing this in a single pass. So I'm again going to enable a ramping distance of 5, an angle of 10, and a Z height of 1. And no tabs will be needed as we're not cutting all the way through. Now all toolpaths are finished for this side of our stock, so we can enable our toolpaths to preview what things look like, and that looks pretty good. Now is a good time to press save if you have not already done so. And we can move on to preparing the bottom of our design. To prepare the bottom, we have to create a new work coordinate system, so that way we'll be able to flip our stock over. So to do this, I'm going to press the plus button to enable a new work coordinate system, and I'm going to rename this coordinate system to be bottom. And then we have to select the origin point for what the bottom will be. Now you'll see that the default origin point is in the top left corner. So what we need to do is select where the top left corner will be when we flip our stock over. So if I rotate my stock in a sort of horizontal fashion here, you can see that this corner will be the top left. So I'm going to choose that as my work coordinate system for the bottom. Once set, we can press OK, and you'll see that we now have this new tab in our layers panel, where you can flip back and forth between the top and the bottom. And when you're on the bottom, you see a preview of your graphics from the top. I'm going to hide the toolpaths on the top, so that way all we see from the bottom is our design file. With that set, we can then import the 2D design for the bottom of our spinner. Now, as these design files were made together, they should automatically align like so. But if needed, you can use the center to center feature to align these designs. It's also important that any offsets are set uniformly in CAM and not done later, as we'll discuss when we go to configure our jobs. This is so that way the design files will align when the stock is flipped based on our alignment holes that we've drilled on the top of our design. Now, the first toolpath that we need to create for the bottom is going to be our engraving path that engraves all the different design features on this side of the spinner. So to do that, I'm going to select all the triangles in my design, as well as select the logo on our two end caps. With these parts of our design selected, we can create a vector pocket toolpath. We're going to engrave from 0 to 0.4 millimeters. And we need to select our engraving bit to do this. So I'm going to delete my flat end mill that I have already preloaded, and I'm going to head over to the engraving bits for metal and select the 0.3 millimeter by 30 degree engraving bit with aluminum set as our default parameters as we did earlier on. We don't need to adjust any of the default parameters, but you might need to change your tool number. I'm going to use the same tool numbers that I used for the top, so I don't need to reload my tool changer for the bottom design file. We don't need any offset for this, so if you have an offset enabled, make sure that that's removed. That might have been from the path that we created earlier on. And we are going to again use ramping using the same 5 millimeter distance, 10 degree angle, and start height of 1. We can then press calculate to preview this toolpath. The next thing that we have to do is create the hole in the center, which is where our center rod is going to pass through. So I'm going to select these two center circles in our design, like so, and then create a vector pocket toolpath. Our start depth is going to be 0, and our end depth is going to be 3.5 millimeters, so that way we pass all the way through. We're then going to select our 3.175 by 12 millimeter flat end mill that we used earlier on, and we don't need to change any of the default parameters, but you might need to adjust your tool number to make sure that you match what you did on the top side of your stock. We're going to use the same strategy and ramping that we did earlier on, so you can simply press calculate to calculate this toolpath. Next, we're going to create some larger pockets, which is where we're actually going to be able to hold our fidget spinner from. So I'm going to select these two larger circles and create another vector pocket toolpath. We had to do this separately because we're going to use a different end depth. This one's going to start from 0 millimeters but end at 1.5 millimeters. However, all the other settings should remain the same. So 3.175 by 12 bit with our aluminum parameters and the same tool number. We're going to use the same strategy, and we're going to use the same ramping technique. After pressing calculate, we can see our toolpath is generated. Now, the last toolpath that we're going to do is going to actually cut the parts out of our stock. And we're going to do this in a slightly clever way in that we're going to create both a chamfer and cut the parts out all at the same time. To do this, go ahead and select your outlines for all 4 parts. Then create a vector contour toolpath. Our start depth is going to be 0, and our end depth is going to be just 1 millimeter. If you remember, we cut all the parts out from the top to a depth of 4 millimeters, meaning that there's only 1 millimeter remaining for our 5 millimeter stock. For our bits, we are going to use our chamfering bit. This is going to machine both the chamfer and cut through our stock to release the parts. You can't typically use a chamfer for a full contour cut, but because we're only machining a millimeter of material away, we can get away with this and create a multi-versatile toolpath. We're going to use the same parameters as we did earlier with a step down of 1 millimeter and slower feed and plunge rates, as well as make sure that our spindle speed and our tool number matches what we did earlier. Likewise, we're going to offset negative 0.5 millimeters from the outside of our path, and make sure that ramping is enabled. Now you could use tabs, although that wouldn't give you the cleanest finish using the chamfering bit. Instead, I'm going to use double-sided tape to secure my parts, as I'll show you later on. So we can just press calculate to calculate this toolpath. With that done, let's head back over to the top and enable our paths, and then we should be able to preview everything in our design here. We're now ready to export our toolpaths, and we're going to have to do this separately for both the top and the bottom. So from our top coordinate system, I'm going to right-click Path and save all toolpaths, and export that as a G-code file to my computer. Then I'm going to switch to the bottom, right-click Path, click Save All Toolpaths, and export these as a G-code file to my computer. Now before we head back to the machine, we do have to create one more part, and we're going to do this using a different material. So I'm going to create a new design file in Makera CAM, and I'm going to create a post that passes through the fidget spinner using a thicker piece of acrylic stock. So to do this, I'm going to edit my material, and I'm going to select plastic. I'm going to use a piece of material that's 100 by 150 by 10 millimeters from the Fidget Spinner Toolkit. Now there's no design file on our wiki sharing site to do this because all we need to do is create a simple circle. So using our create tools, I'm going to create a circle with a diameter of 6.35 millimeters somewhere on my stock. If needed, I can use the transform tools to reposition this so that it's in a nice place without using too much material while also giving enough margin for clamps and fixtures. We're then going to create a very simple vector contour toolpath with a starting depth of 0, an end depth of 10 millimeters, and using our same single flute metal 3.175 by 12 millimeter bit with our plastic parameters set. I'm going to change the tool number to match what I had earlier so I don't need to move my tools around for the two different jobs. Our strategy is going to run along the outside, and you shouldn't need any offset. Ramping is not required, but it's not a bad idea to leave it enabled. Ramping, of course, will just reduce the overall wear on your bits, though a metal bit like this should be able to cut plastic without any issues. Now, I'm not going to use tabs. We are cutting all the way through, but what I'm going to do is leave the plastic on my acrylic when I machine it, so that way it should stay in place and I can just break it away. Alternatively, you could use a double-sided piece of tape to hold your material in place so that you won't have to cut any tabs away for a nice clean finish. After pressing calculate, we can see that we have our toolpaths for our post, so we can simply right-click our path, save this path, and export it as a G-code file to use later on. So with our G-code files prepared, it's now time to prepare our machine for manufacturing. We can secure the stock to the bed of our CNC and make sure that you have a piece of wasteboard as we'll be machining all the way through our stock for the alignment holes and to cut the parts out later on. While I'm using a softer piece of MDF in this video, you may find that a harder piece of material for your wasteboard works better when using alignment pins. And if we're using the Carvera, we need to make sure that our bits are loaded in the automatic tool changer in the order that corresponds to our CAM file. In this case, our 3.175 by 12 millimeter end mill would be in slot 1, our 0.3 millimeter engraving bit would be in slot 3, our 2 millimeter drill bit would be in slot 4, and our chamfering bit would be in slot 6. We also typically don't use the dust tube for metal and instead use the air assist module for chip evacuation and cooling, though this isn't always required. Now with our machine set up, we can head over to the Carvera controller app to configure our G-code files for manufacturing. After loading the G-code file for the top of the spinner, we can press the config and run button to configure this job. We shouldn't need to adjust the offsets, and with a two-sided project, these offsets should be set in the CAM process earlier on to make sure that both sides of your design align perfectly. We do want to enable scan margin. This traces the perimeter of our part before machining, which lets us make sure we're not going to collide with any clamps. Auto Z-probe should be enabled to check the height of our stock automatically, and we can use scan margin to compensate for any deviations in stock thickness by probing the surface of the stock and adjusting during the manufacturing process based on the points recorded. Once set, we can press run. After scanning the perimeter and probing the surface, the Carvera will select the first tool automatically while the Carvera Air will prompt you for the first tool change. The first tool path will be drilling the alignment holes before moving on to the engraving path for the surface designs. The larger pockets will then be machined using the 3.175 by 12 millimeter end mill before running the outline of the parts without passing all the way through the stock. Lastly, the chamfering bit will be used to chamfer the edges of each part. Once the top is finished, we can vacuum away any excess chips, then remove the stock. It's sometimes helpful to remove the corner bracket so alignment with the pins is easier to do. You may also need to vacuum out the pinholes in your wasteboard once the stock has been removed. We also need to apply double-sided tape to the top side to hold the parts in place if you didn't enable tabs. After the 4 pins are inserted in your wasteboard, you can flip the stock horizontally and place it over the pins. You won't need the bracket for the bottom side as the 4 pins will square our part up based on the design. You can then add screws and clamps to each side of the stock to hold it in place securely before removing your alignment pins. And with the material secure, you can then head back over to the Carvera controller app to prepare your bottom files. After loading the G-code files for the bottom part, we can open the config and run window to prepare it for manufacturing. As with the top, we don't want to adjust the offsets, but we do want to enable scan margin, auto Z probe, and auto leveling. Once set, we can click run to start manufacturing. The Carvera will again trace the perimeter and probe the surface of our stock before moving on to the toolpath to manufacture the bottom of our design. This includes the engraving, the smaller pockets, and the larger pockets. Lastly, the chamfering bit will not only be used to apply a chamfer, but also to cut through the stock to release the parts gently. Once finished, we can vacuum away the chips and dust and remove the clamps to peel the stock and parts off the bed of the machine. Be careful as there may be some chips and sharp burrs attached to the double-sided tape, which can be peeled away from the top of the parts. After checking the fit, you can sand the edges to remove any burrs and clean up any unfinished surfaces. And while it's not required, you may also want to add some paint to the pockets and then sand the surface to give you a nice 2-color design with a brushed metal appearance. But before we assemble the spinner, we need to manufacture the acrylic rod using the G-code file that we prepared earlier, and by following the same steps to secure the stock and configure the job as we did with the 2 spinner files earlier on. Now to make this spinner work, we need to install the magnets and the bearings into our 2 parts before we can finish assembly. You should be able to press the bearing in as well as the magnets in place while ensuring they're facing the correct way so that the sides will lock together rather than repel. The magnets will press in, but aligning the spinner may be a little difficult to do if you don't add a small amount of super glue to keep them in place. After installing the magnets in the bearing, you can then place the 2 halves of the spinner together, then slide one of the end caps through the bearing with the acrylic rod pre-installed. Then you just need to attach the second end cap to the other side to finish assembly. And there you have it. There's, of course, many different ways to create a fidget toy, and many of the techniques and processes shown in this tutorial are universally applicable. For example, the same steps that we followed in this tutorial could have also been used to make a simpler single-layer fidget spinner instead. If you make a fidget toy of your own, please share it with us through our community channels. Also, check out our channel and wiki site for more how-tos and guides. And of course, please don't forget to subscribe, and thank you for watching.